Welcome to Norton Chemistry. Today we're going to be doing an equilibrium revision video. I've got an exam question at the end, so make sure to stick around to learn how to apply your knowledge to exam context. So in chemical equilibriums, reversible reactions are represented by the equilibrium symbol, as you can see here. So in this equilibrium, ethanoic acid is dissociating to H plus and CH3CO minus ethanoate ions. And in a dynamic equilibrium, we have certain conditions which are maintained. So there is constant concentrations of reactants and products. The rate of the forward reaction is equal to the rate of the reverse reaction, and it's in a closed system, which means that the conditions are constant and there's nothing added or removed from the reaction mixture. Le Chatelier's principle says that if the reaction conditions of a dynamic equilibrium are changed, the equilibrium will shift to favour either the forward or the reverse reaction in order to oppose the change. So when you're thinking about the effects of changing conditions on Le Chatelier's principle and therefore the position of equilibrium, you need to think, what opposes the change? The effect of a change in temperature depends on whether the forward reaction is exothermic or endothermic. So we know that exothermic reactions release energy to their surroundings, and endothermic reactions take energy in from their surroundings. So exothermic reactions increase the temperature of their surroundings, and endothermic reactions decrease the temperature of their surroundings. If the forward reaction is exothermic, this means that the reverse reaction is endothermic. So for example, in this exothermic reaction, A plus B goes to C plus D, and the enthalpy change is minus 120 kilojoules per mole. That means that the reverse reaction is endothermic, so the enthalpy change of the reverse reaction is positive 120 kilojoules per mole. So if the temperature of this exothermic reaction is increased, the equilibrium will shift in the endothermic direction, so the reverse direction, which is to the left, so towards A and B. And oppositely, if the temperature is decreased, the equilibrium will shift in the exothermic, the forward direction, which is to the right, towards C and D. And this is because the equilibrium shifts to counteract the change. So in the case of increasing the temperature, the equilibrium shifts left to decrease the temperature, because the endothermic reactions take in energy from the surroundings and decrease the temperature of their surroundings, to oppose the change, to decrease the temperature. So changes in concentration. Increasing the reactant concentration causes the equilibrium to shift towards the products to oppose the change and decrease the reactant concentration. And on the other hand, increasing product concentration causes the equilibrium to shift towards the reactants. So you have to think what opposes this change. So for example, we've got HCl aqueous going to ammonia, forming ammonium chloride. So the question is, what would be the effect of increasing the concentration of HCl, which is a reactant, on the position of equilibrium in the reversible reaction above? Explain your answer. So if we increase the concentration of HCl, we increase the reactant concentration, so the equilibrium is going to shift to the opposite direction, to the right, towards the products, because this is going to oppose the change and increase the concentration of the products and decrease the concentration of the reactants. So for pressure, this only applies to gases, and increasing the pressure will cause the equilibrium to shift to the side with the fewest gaseous moles, because this opposes the change. If you increase the pressure and the equilibrium shifts to the side with the fewest gaseous moles, then that decreases the pressure, because you have fewer gaseous moles present. Decreasing the pressure of the system will cause equilibrium to shift to the side with more gaseous moles, opposing the change. So for example, in this reaction, we have nitrogen reacting with 3 moles of hydrogen to form 2 moles of ammonia. So on the left-hand side of the reaction, we have 1 mole of M2 and 3 moles of H2. That makes 4 moles, and on the right side we have 2 moles of NH3 ammonia. Catalysts don't affect the position of equilibrium, but they instead just increase the rate of reaction for both directions, so both the forward and the reverse. So that means the equilibrium is established faster. So we've got a new concept here, which is the equilibrium constant, which we refer to as Kc. And Kc numerically indicates the position of equilibrium, and it is the ratio of the concentrations of the products to the reactants. When we put a reactant or product in square brackets, that indicates the concentration of the reactant or product. So in Kc expressions, we have the concentration of the products divided by the concentration of the reactants to the power of the moles or the stoichiometry of each. So for example, in the general reaction, A plus 2B goes to D plus 2E. A and B go on the bottom as reactants, and D and E go on the top as products. When we have a balancing number in front of any of the reactants or products, we put that as a power to the concentration of that reactant or product. So for example, we have 2B, so that means we do B squared, and we have 2E, so that means we do E squared. The units of Kc vary depending on how many species take part in the reaction and the stoichiometry of the reaction. So for example, in the reaction above, we have A plus 2B going to D plus 2E. And for each reactant and product, we have mole per dm cubed. So on the top of the equation, we have mole per dm cubed to the power of 3, and on the bottom, we have mole per dm cubed to the power of 3. So both of these units cancel out, and that leaves us with no units. It can sometimes be more difficult to calculate the units. So for example, in this reaction, we have 2 mole per dm cubed on the top and 3 mole per dm cubed on the bottom. So we cancel out the top, and that leaves us with 1 on the bottom. And then because it's on the bottom, we have to do the inverse of it. So we have to change the symbol, and that becomes mole to the minus 1 dm cubed. But we usually put it in the positive order first, then the negative. So that's dm cubed per mole to the minus 1. So when Kc is equal to 1, that means that the equilibrium is exactly halfway between the reactants and the products. When Kc is more than 1, that means the equilibrium is shifted further to the right, so the products are favoured. And inversely, when Kc is less than 1, that means that the equilibrium is further to the left, or the reactants are favoured. So we've got an exam question. This question is about ammonia. In industry, ammonia is made from nitrogen and hydrogen. This is a reversible reaction as shown in equilibrium 24.1. So we've got 2 nitrogen reacting with 3 hydrogen to form 2 ammonia. And you'll notice the enthalpy change is exothermic. It's minus 92 kilojoules per mole. Explain how Le Chatelier's principle can be used to predict the conditions of temperature and pressure for a maximum equilibrium yield of ammonia. So let's deal with temperature first. So the forward reaction is exothermic. That means the reverse reaction is endothermic. So we're going to want to decrease the temperature to shift the equilibrium to the right, because exothermic reactions release energy to their surroundings. So if we decrease the temperature, then the exothermic direction will be favoured, because the equilibrium will shift to oppose a change to increase the temperature. And then for pressure, you'll notice we have 2 gaseous moles of ammonia on the right, and we have 4 gaseous moles of nitrogen and hydrogen on the left. So to shift the equilibrium to the right, we're going to want to increase the pressure, because if we increase the pressure, the equilibrium will shift to the right to counteract the change and decrease the pressure. Now you might be asked in exam questions to justify why these optimum conditions might not be used in industry, and this is often for high temperature because it can be expensive and have high energy requirements to maintain, and the high pressure can be dangerous. Using certain conditions, equilibrium 24.1 has the equilibrium concentrations in the table, and they're asking us to calculate the numerical value for Kc under these conditions. Give your answer to an appropriate number of sig fig and in standard form. So the appropriate sig fig is going to be 3 significant figures, because in the table in the question, we're given all of the concentrations to 3 significant figures, and then we need to remember to leave it in standard form. So remembering that the formula for the Kc is the concentration of the products divided by the concentration of the reactants. So our product is ammonia, so that's going to be 0.862 mole per dm cubed. Not forgetting that we need to square it, because in the equation, remember, we have 2 moles of ammonia, and then we need to divide it by concentration of nitrogen, which is 1.25 mole per dm cubed, and that's just the power of 1, and then we have hydrogen, which is going to be 2.75 to the power of 3, and then if you put that into the calculator, you get 0.02858, and then you convert to 3 significant figures and standard form, so that's 2.86 times 10 to the minus 2. Thanks for watching. Make sure to check out my reaction rates revision video, which will be in the bottom right hand corner now. You can also check out my website to purchase my notes and flashcards. The link will be in the description below.